so I think I will start with giving you a rough idea what this talk will be about. So what we want to achieve here is that we want to optimize the random numbers that we use for Monte Carlo integration in order to improve the convergence rate of our Monte Carlo estimator. And specifically, we target here discontinuous integrands as they typically suffer from poorer convergence rates. One thing I want to mention here right in the beginning is that we only focus here on two-dimensional integrands, which means, for example, in the domain of rendering, that we target problems like computing direct illumination or depth of field. Okay, so with that in mind, let's begin with some background here. So when our scenario is that we want to solve the rendering equation, and when we do this with Monte Carlo path tracing, we accumulate multiple samples per pixel. When we only accumulate a single one, then we, of course, get lots and lots of noise, and the typical solution in offline path tracing is then that you just accumulate hundreds or thousands of these samples until you converge to some mostly noise-free solution. The number of samples you require for that, of course, depends first on your importance sampling technique, but also on the rate with which your Monte Carlo estimator converges. Okay, so mathematically speaking, what we're doing here is we integrate over all these paths that connect the light source over one bounce with the camera. Instead of integrating over this path space domain, we can also think about or rewrite this as integrating over this 0, 1 square random number domain, which means that we use some form of transformation to map a point to, for example, a point on the light source or to a direction on the hemisphere. Okay, so now let's move on and let's take a look how different structures of integrands in this 0, 1 square domain influence the convergence rate of our Monte Carlo estimator. And for that, I'm showing you here 3 examples of the variance and with how it converges for 3 different integrands, 1 smooth and 2 with discontinuities. And when we just use random sampling, you can see that we always get the suboptimal convergence rate of n to the minus 1. But instead of using random sampling, we can also introduce some correlations into that pattern. So we use quasi-Monte Carlo integration. And we can see now that we get exceptional convergence behavior on smooth integrands. But for discontinuous integrands, this convergence rate drops. In the case that this discontinuity is at least axis aligned, we can see that we get still pretty good convergence behavior. But for arbitrarily oriented discontinuities, we can see that this convergence rate drops significantly. So what we want to solve here in this paper is the question whether we can get better than this poor convergence rates on arbitrarily oriented discontinuous integrands. For that, we first need to take a look at some prior work which analyzed the variance in quasi-Monte Carlo integration. The idea is, or what they did is, they take the sampling pattern and the function they want to integrate from the spatial domain, applied a Fourier transformation to that to get the respective power spectrum in the frequency domain. And what they found out is that the variance of the Monte Carlo estimator is actually just the product of these 2 power spectrum, then evaluated at all integer frequencies except the 0 frequency. And you can see this here in this visualization, that here this picture is very dark of this product power spectrum, which means that there is only low energy remaining, which means that this Monte Carlo estimator suffers from low variance. In contrast, if you have a different function you want to integrate, and if it doesn't match that well with the power spectrum of the sampling pattern, you still have high energies left, which means that the second Monte Carlo estimator with the same sampling pattern and the same number of samples suffers from higher variance. Okay, let's continue this a little bit and take a look at some examples of discontinuous integrands and also sampling patterns to understand it a little bit better. Here, the first example I want to show you is this vertical discontinuity. And you can see here that this step function, which is mathematically, is made up of all these, of an infinite amount of increasingly higher frequencies. So we need all of them to reconstruct this edge. Now, for a diagonal discontinuity, you may think that you only get high energies along this diagonal, but in fact, due to this finite integration domain and the toroidal behavior of the Fourier transformation, which we can think of as repeating this integrand over and over again, we can now see that we also get discontinuities along the horizontal and vertical direction, and we need to have a sampling pattern which matches with all these 3 high energy directions in order to reduce variance. Okay, moving on to sampling patterns. Here for random sampling, this is just white noise, so you have all frequencies in your power spectrum, but we can also do something like in stratification approach, where you put or ensure that only one point is in each of these horizontal and vertical grid lines. And with that, we can see that this approach already suppresses frequencies along the horizontal and vertical direction very effectively. Okay, prior work now tried to exploit this anisotropic structure of these existing sampling patterns. And their idea is, instead of just using the sampling pattern as it is, they propose to apply a shearing operation to all these points in the point pattern, which also effectively then shears these strata in which the points are aligned. And we can see here that in this specific case now the power spectrum of the sampling pattern matches much better with the power spectrum of the function we want to integrate. And with that, they show that they can reduce variance in these cases. The general problem here, however, is that these existing anisotropic patterns only have two low energy directions. But as we've seen here on the slide before, even for simple diagonal edge or discontinuity, which isn't uncommon in rendering when you think about shadow edges, then you already get three high energy directions, and we can clearly see the mismatch here. Okay, so this is what our paper now tries to solve. So our idea here is that we want to optimize point sets which anisotropic with anisotropic power spectra, which can suppress frequencies along multiple directions. So we want to ensure stratification along more than two directions. Okay, so how do we do this? Our idea here is that we just use a standard gradient descent solver or optimizer. And of course, for that, we need some kind of objective function, which we can put into this optimizer, and then it optimizes this function. And we can see here that our objective function here in this case is made up of these two terms. And the first one is this spectrum objective. And there, the user can just provide a set of frequencies they want to suppress. And then in each iteration of our optimization process, we just compute the current power spectrum at this frequency and compare it or make sure that it goes to zero. Since computing this power spectrum is rather expensive and we only want to do this for a small finite set of frequencies, we add a second loss term here, which is this sliced Wasserstein loss, which corresponds to 1D optimal transport. And this ensures that we get these correct 1D marginal distributions so that we ensure stratification along these few directions we want to optimize for. Okay, let's take a look here at some results. So first here again an existing point pattern here with 4,000 and 65,000 points in the set. And we can see here that these existing points as set have only these two low energy directions. And we can shear them, but still they have only two of these directions. Now when we run our point optimization algorithm, we can see here that we can suppress frequencies along three directions, or in the second example here, we can even do this for four directions, and in the paper we show this also for more directions. Okay, so you now may wonder, how do our points look like? And we can see here that they do not look that different from existing point patterns. So we still have nicely and evenly distributed points with uniform density, so this is very good. Okay, let's take a look here at some convergence plots now. Again, I'm plotting here the convergence rates of the variance of the Monte Carlo estimator. And here we want, again, integrate this 2D discontinuous function with this arbitrary orientation. And we can see here when we use an existing point pattern, which can only align with two of these three high energy directions, that we get this expected poor convergence rate. We can, of course, apply this shearing idea of prior work. And we see here that it doesn't matter for the convergence rate, because in this case now we do not match with the horizontal anymore. Now, however, when we use our optimized point sets, which can cover all three directions, we can see here that we can significantly improve the convergence rate of our estimator. And this, of course, is not limited to only three directions. Here I'm showing you this with two differently oriented discontinuities. This is the purple line here, and we get, again, this improved convergence rate. And also we can, of course, also make this integrand a bit more complicated. So we applied here a low frequency pattern to that. And we can see that we also eventually get to this improved convergence rate. Okay, so the main motivation here was that we want to apply this to rendering. So I want to spend the last few minutes to explain to you how we apply this to offline path tracing to compute direct illumination here with area light sampling. So our scenario here is that we want to render the image here on the left side. And each pixel, of course, has some underlying function that we need to integrate and some power spectrum associated with it. Of course, unfortunately, this is unknown before rendering, and we need some cheap way to estimate these high energy directions in the power spectrum. To make things a little bit simpler, and because it is true most of the times, we just assume from the beginning that we always have high energies along the horizontal and vertical directions. But for all other directions, we need to detect this somehow. And our idea here is that we amortize this cost over blocks of pixels. So what we're doing here, we cooperatively in blocks of pixels sample this integrand at a low resolution. Then we can apply some smoothing kernels to that and edge detection kernels to get a histogram of these occurring edge orientations. This histogram is of course noisy, so we do not just want to take the maximum direction, but our solution for this is that we instead fit the mean of multiple von Mises-Fischer distributions with a mode-seeking objective, and you can see this plotted here on the bottom right. And you can clearly see here that these local minima correspond exactly to the positions where we want to place our von Mises-Fischer distributions. Okay, so with that, we have extracted this information about these high energy directions. So in theory, we can just run our sampling point optimization and get a matching point set for each pixel in this block. However, this point optimization algorithm, and I think some of you may already think that, runs offline, so it can take several minutes to optimize a point set depending on the number of points and the number of frequencies we optimize for. Our solution for this is that we are able to just pre-compute point sets offline in 1 degree steps. So we have sets of these points, so we have point sets which can match with, for example, 3 directions, so the horizontal, the vertical, and some arbitrary direction, and exploiting some symmetries. We only need a few of these sets. And then also with 4 directions, so 2 arbitrary directions. And as you can see there in the footnote, we still are able to put this into, or upload this to a GPU, for example, when we render on the GPU. And then we can just select the matching set during rendering, apply some Craney-Patterson rotation to that to decorrelate between pixels. And with that, we can then improve variance. Okay, so let's take a look at some renderings here. So that I can convince you that this is in fact working. So here I'm showing you on the left side a close-up of this Cornell box scene with area light sampling for direct illumination, and I'm plotting here the variance after 4,000 samples per pixel. And you can see here on the right side that most of these integrands in this scene have a few straight discontinuities, which means that we have power spectra which have at least 3 high energy directions. This means when we use an existing point pattern, which only can suppress 2 of these directions, that we get high variance. Using the shearing idea from prior work still gets mostly the same result. But we can see here, when we correctly estimate these high energy directions, that we can significantly reduce the variance here in this region where this shadow is. When we extend this a little bit and also detect a second orientation of this second edge here in the top right corner where you have 2 differently oriented shadow edges, we can see that we can even reduce variance there when we use a point set which can cover all these 4 directions. Okay, so this was for area light sampling, and in area light sampling you typically have a few straight discontinuities, but we also want to make this work for hemisphere sampling. So we've taken a look at this, and I'm showing you an example here where you can see that we, of course, still have discontinuities due to occlusion, but in this case, these discontinuities are typically curved, which makes it clearly impossible to align with since all energy is distributed across all directions. Our solution for this is that we can apply some low distortion mapping to this integrand. here in our case an octahedron mapping, and you can now see that we again get an integrand which has only a few straight discontinuities, which makes it possible to align with. And if you're interested into that, you can take a look in the paper where we show that we can, with the same number of samples, again get reduced variance and a better conversions rate. Okay, so we've seen here that by estimating these orientation of discontinuities, we can get better conversion rates on 2D discontinuous integrands. This does not solve everything, of course, so there is still some future work left. For example, the first thing is replacing our pre-computation of the point sets with some online point optimization algorithm, then reducing the overhead of this estimation of these high frequency, high energy directions. And lastly, there's this future work question whether it's viable and possible to learn and align with discontinuities even in higher dimensional light transport. And with that said, thank you for your attention.
Thank you. We'll take questions now. Right here.
Thank you for the presentation. Can you go to like page 14?
Oh yeah.
Yes. I'm looking at these distributions. I can see there's an obvious bending effects, or some corner like have much less samples. Like, so we can see this like a very bright white, this very hard edge. Do you know where this come from?
In which corner do you mean? So in the power spectra, or
yes, the power structures, the noise image.
Yeah. So along these directions, or in this grid structure behind that, or what do you refer to?
Yeah, like along the low energy anisotropic directions, like this black. Around this black, you can see there are some white, very bright.
Also in the power spectrum of the points. Yeah. Okay.
Yes, exactly.
Yeah, exactly. So these are. So what we are doing is we just try to suppress the frequencies that the user defined or that fall into our sliced Wasserstein optimization. So in that directions, and for the other, typically you get only you get white noise there. Mm-hmm. But in this case, it seems that we choose too many frequencies to suppress, and with that you get some aliasing artifacts, or you enforce that the points are in some repeating pattern, that you get these higher energies in these other frequencies there. But as most of these most of these integrants that we want to integrate do not have high energies at that point, it doesn't matter that much, I would say. But yeah, you can reduce, you can try to optimize for less frequencies, and then you can, I think, reduce these artifacts.
Okay, thank you.
Any other questions? Right there.
Thank you very much for your talk. I have a question. Have you tried to use your sampling pattern in higher dimensions by simply using it component-wisely or block-wisely on consecutive two-dimensional blocks?
Not yet. This is for future work, so great idea, of course. So what would be a natural way to try this would be, for example, to just say, okay, we align with the first two dimensions, and then we do something like hemisphere sampling, and then we say everything else on the higher dimensions might be smoothed out. So this can, from my understanding, maybe improve variance, but this is definitely something we need to investigate more and thoroughly evaluate, which we didn't in this paper until this point.
Yeah, it would be curious to see. Thank you.
So do you think that your technique could work if you have like high frequency shadows, so in an area in your scene where you have a lot of shadows and very thin shadows?
Okay, so you mean you have lots and lots of these discontinuities?
Like, for example, think about a tree with many leaves.
Yeah, so this clearly is a limitation of the method. So if the edges you want to detect in your integrand are, of course, so small that you are you just do not have the resolution to do this, then it clearly fails. So either you increase the resolution when you sample this pixel, when you sample this integrand, and then you can still detect this orientation of edges. But then you also need sampling patterns which suppress frequencies along more directions. And we also show this in the paper that we can do this or we can extend this idea to more and more of these directions. But your variance increases a bit. You still get this good convergence rate, but your overall variance increases because you cannot suppress all these frequencies that well anymore along each direction. So yeah, so if you have too many directions, this method clearly doesn't pay out. It makes only sense if you have only a small set of these straight discontinuities.
Thank you.
Thank you very much for the very good talk. I wanted to ask, have you ever thought about, or does it even make sense to think about training some ML model on some D-series synthetic data, and then just, instead of just doing shear transformations, we can even do more complex transformations on the quasi-Monte Carlo samples?
So you want to train a neural network which predicts these points or optimizes these points?
The distribution of the quasi-Monte Carlo.
Yeah, okay, so we do not want to change the distribution, only how they are stratified, but the other thing would be important sampling, I guess. Yes, so prior work also tried this with neural networks to optimize these point sets, and they showed this, for example, for blue noise point sets. So we also tried their methods, but then you need a neural network which generalizes over multiple directions you want to optimize for. So I think it would be possible. Our method now is really easy to implement and fast to compute because we directly optimize these points with a standard atom optimizer, for example. But sure, if you have a large enough network which can optimize your points with or you just say, okay, I want to optimize or suppress these frequencies along some target angle, then it might work too, yeah.
Thank you.
All right, any more questions? All right, if not, then thank you again.